We're now going to turn to integration of functions of more than one variable. Now, unlike with functions of one variable, we don't look at indefinite integrals. So we will always have limits of integration. Furthermore, the limits of integration, instead of just being integrating over an interval, like say for example the integral from a to b f of x dx, so this definite integral right here where we would integrate on the interval a to b of some function to get the area, now in integrating functions of more than one variable, we now integrate over a region. So now if we look at our domain of integration, we integrate now with respect to x and y, we now can have some strange region over here over which the top of this, if we're looking down from above, our region would maybe be the height. So now we're looking at the integral of the height as a function of two variables, and this might give us the volume of the region. And that makes the limits of integration a little more complicated than we had in Calc 1 and 2. Let's start out maybe just with an example of one of these. This two-dimensional integral right here is called an iterated integral. Iterated because we do the integral and then we integrate again. So an example of this might be the integral from 0 to 3, the integral from 0 to x of xy dy dx. I just want to point out here that we do the inner integral first. So that's this inside integral right here. So this inside integral is an integral with respect to y, and its limits can depend on any of the outer limits of integration. So we're integrating with respect to y, the limits can involve x. So let's go through and do this integral. Now remember, just like with partial derivatives, we're going to treat the x like a constant in this case. So this will give us the integral from 0 to 3. X is constant, so it just sits there and we get y squared over 2. And now our limits of integration, just to ease the record keeping here, we might want to say the y's go from 0 up to x. And then we still have the outer integral to contend with afterwards. So if we plug in those inner limits of integration, we plug in x, we get x cubed over 2, minus, we plug in y equals 0, we get 0. And now this looks like a familiar integral from Calc 1. So we just go in through and use the power rule again. So we get x to the 4th over 8 from 0 to 3. And this gives us 3 to the 4th over 8 minus 0 to the 4th over 8. So we get 81 over 8. So this is sort of a standard iterated integral. Now some iterated integrals, we can't do them in the order in which they're presented. We have to do a little bit to switch the order around. Let's look at an example of this. Say we've got the integral from 0 to pi, the integral from x to pi of, let's say, sine of x squared. Now let's make the sine of y squared dy dx. So if we were to look at this integral as is, our inner integral says to integrate with respect to y. However, this integral of sine squared, we can't actually do. So we need to do something to switch the order of integration around on this. So if we make a sketch of the region of integration, the x value is going from 0 to pi. So we're integrating from x equals 0 to x equals pi. And then the y, given an x value, the y's range from y equals x, so this is the line y equals x, up to the line y equals pi. So our region of integration is this triangle in here. Now I want to switch the limits of integration around. So I'm going to swap this. So I want to integrate y on the outside. That means y has constant limits of integration. If I look at the lowest y value anywhere in this region, it's y equals 0. And the highest y value anywhere in here is pi. So it's convenient. It has the same limits, but for a different reason. These are in the original integral, those were x limits. In this new integral, those are y limits. So we integrate from 0 to pi. Now, given a y value, the x's range from this line here, from x equals 0, out to this line, x equals y. So our limits of integration are now 0 to y. And now the integrand stays the same. That never switches when we alter our limits of integration, when we flip them around. However, now this inside integral is with respect to x. So if we integrate that with respect to x, sine of y squared is constant. It has no x's in it. So we integrate and we're going to pick up an x. And x we evaluate from x equals 0 to x equals y. Now when we plug those in, we plug in x equals y here. We've got y sine of y squared minus 0 sine of y squared dy. And now this second part of the integral drops out, and this first part we can actually do by a u substitution. If we let u equal y squared, then du is 2y dy. So I have a y here, but I need a 2. So we'll multiply the inside by 2 and divide the outside by 2. So this gives us 1/2. Now the integral of sine is negative cosine of y squared, evaluated from 0 to pi. And now we're going to plug these in. We plug in our upper limit first, and we get negative 1/2 cosine of pi squared plus 1/2 cosine of 0 is 1. So this gives us our answer for this iterated integral after switching the order. And now, if we have an integral that we can actually evaluate in both orders, they should match. So these two quantities should be equal. Although we couldn't actually do the integral as written, we know that it will be the same value, 1/2 minus 1/2 cosine of pi squared. So that's the gist of iterated integral as a function of two variables.